Ja, ich glaube schon.
Hi. It's my great pleasure to introduce Maria Eckstein, right from London, from DeepMind. And yeah, Maria did her PhD at UC Berkeley, where she worked on pupillometry and how that relates to inference. And yeah, now she's doing a lot of work on cognitive modeling over age and yeah, lots of yeah, fitting models to human data, which is really at the core of our summer school, I think, and where we also, for example, have the hackathon topic on Thursday related to that. So yeah, without further ado, stage is yours. Thanks for being here.
Thank you so much. Okay, I just want to show you guys those two videos, and you can take a look at them, and then tell me, what do those have in common? Play, that's a good one. Yeah? Trial and error learner, that's really good, really good. What else? Fun, yeah, definitely very related, 100%. Interaction, yes, lots of interaction, that's crucial. Special processing of, can you say of what?
On the left video, you need to move the line. Depends on the position of the ball, and in the right video, the dogs jump on the place.
Yeah, that's good. Yeah. Timing? Yeah, we will talk about timing. Learning, yeah, very good. Learning is crucial. Yeah. What did you want to say? Learning.
Interactions between an environment and model or.
Okay, perfect. You guys all got it. This is great. This is exactly what this talk will be about. I'll talk about reinforcement learning, which is all of those things that you just mentioned. It is the interaction between an agent and an environment based on rewards. And so basically, when you think about, let me just start this again. When you think about this video here, this is an Atari agent that was made by some of my colleagues at DeepMind, and that plays Atari at superhuman performance. And this obviously is a dog who's learning tricks. And the whole premise of cognitive modeling is to try and use algorithms like this one here that we know what they look like because we literally have access to the Python code, and try to understand what might be going on inside this dog's mind, which we don't have access to because this is a black box. We just don't know what's happening here. Okay, so reinforcement learning is just learning from rewards, learning to execute actions from rewards, learning not to do something if you get punished for it. And the way this looks like in the lab is we pretty much define a goal. So for the Atari agent, we say we want the Atari agent to maximize the score. For the dog, we say we want the dog to stand on my feet. And then we need to think of a reward. So for the Atari agent, we might say each point is one reward. For the dog, we say, oh, like gaining treats is a reward. And then we need some ingredients, and I'll talk more about this later, but I want you guys to already be familiar with this lingo. We talk about actions here. So actions could be moving the pedal left and right. And we talk about states. So this environment can be in different states, right? You can have a lot of tiles or very few tiles. The pedal can be in different locations. This is what we call a state that's crucial for RL. And then we also talk about rewards. And now we can use this framework of talking about actions and states and rewards that we need for the Atari agent and translate it to the biological agents. So now we can say actions are jumping and standing, states are raising my legs up or not raising my legs up as a symbol for the dog to jump, and rewards could be nothing or the treat. And now the crucial part is that when we train this agent, we know exactly what's going on because we have hard-coded the reinforcement learning agent. And I won't talk about this too much right now because the rest of the lecture will be kind of going through those equations. But pretty much what we are saying here is that we have a value. Each action that we could take has a specific value, and we learn those values over time. And this is what allows us to choose the best action at each moment. And now what we do in cognitive modeling is we say, we don't actually know what is going on inside the dog's mind, but we know what is going on inside the Atari agent. And because there's a lot of similarities between those two, like you said on the last slide, all those things they share in common, we make this leap of faith and say, what these equations might also apply to the dog. So this is the whole premise of reinforcement learning. This is the whole premise of cognitive modeling. I just gave you the introduction, and I will next talk about RL from a psychology perspective. And then I want to talk about RL from a few different perspectives, from an AI perspective, from a neuroscience perspective, and then I want to bring it all together and talk about cognitive modeling or using RL as a cognitive model. So you all have heard of classical conditioning, I'm sure. All the classical conditioning is telling us is we might have unconditional stimuli that lead to an unconditional response, and we might have neutral stimuli that don't lead to a response at all. But when we pair the neutral stimulus with the unconditioned stimulus, and we do that time and time again, at some point, the dog will also respond to the now conditioned stimulus with the now conditioned response. So here, if you whistle, the dog will salivate because he's expecting food. And in 1972, Rescorla and Wagner thought about this and thought, okay, this is pretty obvious, but why is this happening? Like, what is going on? Can we write down can we set up a theory that explains really what is happening? Can we write down some equations that tell us how this is taking place? And so what they did is they basically say that all stimuli have an associative strength, which now in modern RL we call the value. And basically what this associative strength tells you is if this reward will predict, if this stimulus will predict a reward. So for the whistle in the beginning, it has associative strength of 0. There's no reason to believe that the whistle will predict food. But at the end of conditioning, the whistle will have a really high associative strength because we have learned every time the whistle is blown, we will get food afterwards. And the interesting thing now is we can use this associative strength that we have learned for all the stimuli in the world to make predictions about what is going to happen next. So if I hear the whistle, I will predict there will be food. And if there's no food, I will experience a reward prediction error. I will experience a prediction error. So now we train our brain to constantly make predictions, and then we compare those predictions to what is actually happening. And whenever we observe an error, a discrepancy between the two, when our brain predicts something that doesn't actually happen, we experience a reward prediction error. And the important thing about the reward prediction error is it triggers learning. This is the whole premise of RL. Whenever we experience a prediction error, or we predict something, and it doesn't actually happen, something else happens, that's when the brain knows, dude, now we need to do an update. We need to learn. We need to get better at predicting the world. And this is obviously in order to predict better when we get reward. So they came up with this equation here. So what we do is first we need to calculate a reward prediction error. And the reward prediction error is just a discrepancy between what actually happens. Lambda here is just saying, we got food, we got a reward. And then we compare that to the associative strength of all the stimuli in the environment that could have predicted that reward. So was the whistle blown, yes or no? Is it lunchtime, yes or no? Is my owner present, yes or no? Like all the stimuli in my environment, I add all of them up to say, how likely am I going to get food right now? And then I compare that to, did I actually get food? And this will give me an error or not, which is called a reward prediction error. And now what we do is we can learn. We can look at the values of all our cues, the whistle, lunchtime, presence of the owner, and we can say, okay, there was a big error. There was food and I didn't expect it, but there was no food and I expected it. And we can update the old value. I can calculate a new value based on the old value plus the reward prediction error. And the reward prediction error will be scaled by two by two variables here, which is the salience of the CS, so say how loud is the whistle, do I even hear it, and the association value, like how much do I even like the food. And now in modern RL, we only have one parameter here, which we call the learning rate, but this is kind of the birth of reinforcement learning. This is the first time that people actually tried to put equations on this really simple phenomenon of Pavlovian learning. Okay, so this is where it gets a little interactive. So let's just walk through this example. Before conditioning, the dog hasn't learned anything yet. The dog is naive, just comes into the lab. What's the value, the associative strength of the whistle or of the bell? Zero. Lambda just means, I mean, I'm telling you here, lambda is 1. Lambda just means, is the unconditioned stimulus present or no? So in this case, while we do the conditioning, lambda is present. So we set it to 1. What's the RPE? What's the reward prediction error? 1. Exactly. It's just this difference between those two, right? It's just lambda minus the sum of all the values. Okay, so what's the new value? Let's just assume that those two scaling parameters together are 0.5. 0.5, exactly. We take the old value, which is 0, plus 0.5 times 1 for the reward prediction error. Nice. Okay, so now let's do another iteration of that. We just do the same thing again. We just repeat what we just did. The old value of the bell, are there any, do you have any questions? All good? Okay, cool. So yeah, feel free to shout out if you have any questions. So we start with a value of 0.5 this time. So what is lambda? Same as before? 1 again, we have the food. What's the RPE this time? 0.5. And what's the new value if you go through this equation again? 0.75. Wonderful. Okay, and we could keep doing this, right? Like we could keep doing this. Let's do one more. 0.75 lambda is 1. What's the RPE? 0.25, new value, and so on. So where will this go? If you repeat this like 1,000 more times, you see how this value gets bigger and bigger and bigger. Where will it asymptote towards? 1, exactly. Will asymptote towards the value of lambda. Great. So what's the prediction of this theory? If I say the value of the bell is 1 at the end of this whole thing, what does the theory predict if you present the dog with the bell? What will happen?
Always expect the reward.
It expects the reward, exactly. And this is how it explains all of the phenomena of classic conditioning. Now the whistle has acquired a value of 1, which means the dog expects the food, which means the dog will salivate. Okay, perfect. So now let's do one more example that is a little more interesting. So let's say we have trained the dog, just like we did. The value of the bell is 1. And now what we do is we add another unconditioned stimulus. We add a light in there. So now there's always a light and the bell that come on at the same time, and then the dog gets food. Does it make sense as a setup? Okay, cool. The dog has already learned that the bell predicts food, and now we also have the light. So let me ask you, if we do this, say 100 times, we now always have the light and the bell and then the food. Now we only present the light. What will happen? Will the dog respond or will the dog not respond? Let's do a quick vote. Who thinks the dog will respond? Okay. Who thinks the dog will not respond? Okay, pretty even. We're pretty evenly split. Okay, let me ask you a different question. Based on this theory, based on these equations, will the dog respond or not respond? Who thinks that based on these equations, what we just learned, the dog will respond? And not respond? Okay, pretty even. Okay, so let's walk through this example. Let's walk through this example and see. So we start, value of the bell, what is it? 1, because we already, what's the lambda? 1. RPE? 0. 0 RPE means no learning. No learning, right? Okay, so now let's walk through the next example where we also have the light. Value of the bell is 1. What's the value of the light? 0. What's the sum of all the values of all the CS present in the environment? 1. What's lambda? What's the RPE? 0. What does it mean for the new value of the bell? What does it mean for the new value of the light? 0. So what does it mean for the response of the dog in response to the light? The value of the light, if you repeat this 200 times, 1,000 times, what's the value of the light? Will always stay 0, which means, I just showed it to you, this theory does not predict a conditioned response. Isn't that odd? And actually, people have done these experiments in a lot of different animals and also humans, and it turns out a lot of them do show this blocking phenomenon. So if one stimulus is perfectly predictive, we won't learn about any other stimulus, pretty much. And this is really cool, and this is why people like this theory so much, is because it can really make those qualitative predictions of how animals or how humans will respond. Okay, so this is pretty much the psychology perspective on reinforcement learning. We can do the same thing we just did for classical conditioning for operant conditioning as well. So like when I have a rat that needs to press a lever, I can use the exact same theory to tell you how the value of the lever pressing will increase over time. But this is pretty much psychology. So of course, there are many more memory systems, and this is just one memory system of simple classical conditioning. But we have a lot of other memory systems, non-declarative memory. We don't want this software update right now. And of declarative memory as well. And there actually now is a lot of research that tries to bring all of those different memory systems together and come up with equations for all of those and not just RL. But I will specialize in RL right now because there's a lot of research happening there. I just want you guys to know that there's a lot of things that are not just RL. Okay, do you have any questions? Yeah.
Can you explain why the second student value of the light was 0?
Yes. Here?
Yes.
Why is it 0? Because we assume that the dog has no reason to expect the light to predict food. Exactly. In the first experiment, there was only the bell. So here, we only had the bell. And at the beginning, the value of the bell also was 0. It's as if I say the value of the window open or closed is 0, because there's no reason to expect that the open window will predict food or a closed window will predict food. It's just totally random. Why would a whistle predict food? Why would a bell predict food? Why would a light predict food?
We would do a second iteration with light and bell.
Mm-hmm.
With okay, I get it. So then the theory says the value of the light stays 0.
Exactly, yeah. Yeah. Yeah.
So it said theoretically that works, but he also said empirically there are some cases where it does follow this theory, but is that, can you give us a tendency?
Yeah. Yeah, it's very often. So this is one of the prime arguments for Rescorla-Wagner, is that animals tend to show blocking in this way. So animals usually do this. And there's a few experiments where people have not found blocking, but it turns out once you set up your experiment in the right way, usually you find blocking. So this is where the nuance comes in. But so far, pretty much when people have set it up in the right way, they usually see blocking. So they usually see exactly this behavior in a lot of different animals.
does it change something if you change the value of alpha? Because that alpha is now weights, let's say, the different the value of bell and the value of alpha.
Yeah, I think it definitely would. I haven't walked through that, but I'm sure it would change things. So as long as we don't have a reward prediction error, as long as the RPE is 0, changing those two wouldn't make any difference at all. But say, but if there's an RPE, then the alpha would make a difference. There's one thing that will make a difference, and that is if we swap the order of the things, right? Like right now we're presenting them simultaneously, but you could imagine the light comes on, and then 2 seconds later the bell comes on, and then 2 seconds later the food comes on, right? And in that case, the light would get all the predictive strength for the bell, which would get the predictive strength for the food, and in that case, you would increase your associative strength. Yeah.
What would happen if I train the dog with the two stimulus at the same time?
What would happen? I wonder. Yeah.
Just the light.
So just the light, or the light and the whistle from the beginning?
No, just the two from the beginning.
Two from the beginning.
And then I turn, and maybe I turn.
Yeah. Yeah, that's a very good question. Let's walk through that. So basically what you're saying is we start from scratch. The value of the bell is 0, and the value of the light also is 0. That's what you're saying, right? We start from scratch with both of them. So then the sum of all of them would be 0, lambda would be 1, and the RPE would be 1. And so now we update both of them, right? Because we have an RPE. So the new value of the bell would be 0.5, the new value of the light would be 0.5. And so now both would get updated. You will have a different learning curve because now you always have the sum here. So if both of them already are at 0.5, on the next trial, you will already predict 1 and your work will be 1. So there won't be any more learning. So both of them will plateau out at a much lower value. They won't go all the way to 1, they will like stay halfway. Which makes interesting predictions because now you don't expect the food to salivate just as much, like only halfway as much, but for both. Yeah.
Is there empirical evidence for this kind of staying at a lower value, so that does not, because you could also think that maybe the dog makes some kind of categorical decision to just put both to 1 if they are. If it makes sense.
No, that's a great question, and there definitely are some studies that show exactly that. It's easier for operant conditioning when the rat is pressing the lever, because then you can just count in a 1 minute time window how often does the rat press the lever, and maybe the rat has learned about 2 different levers or something, so you can just count, and then you actually see that it's not as high, but it's like it's lower. Yeah. Yeah.
That's a bit of a far stretch, but could this explain the tendency for us to not accept a new model of something we already learned? For example, relearning something, or not being open-minded about the concept because the old system already works for us.
I think that's really interesting. You should do a study on that. I would love to see that, because I think you could set it up in a nice way. If there already is an explanation for something, you might be more reluctant to accept a new explanation because you already have a working explanation. That would be super cool, yeah. Okay, and I think this will be the last question, and we move on. Yeah.
If you condition the dog to react to both, at the same time, and then only present one of those, would it also lead to salivation of the dog? Or?
Yeah. If you train on both, and then you only show one, the dog will respond. It will just respond more weakly in a weaker way. Yeah. Okay, wonderful. So now let's talk about AI. And this is the part where it gets a little technical, but bear with me. This is basically putting all of that into the context of how those equations actually work. So do you guys have a background in machine learning at all? Okay, cool. So what am I showing here? What is this? Yeah. Clustering, cool, which is a kind of wonderful unsupervised learning. So what could this be? Supervised learning. What could the third category be? Reinforcement learning, wonderful. So this is just to situate us in the world of ML, what we are talking about now. Cool, so RL has ingredients. RL needs an agent. The agent is the dog, is the Atari agent, is whatever, that learns a policy. A policy is a mapping from states to actions. So basically we look around, where are we, and then we decide what to do. That's a policy. It tells us how to act in the world. We also need an environment. An environment can be a lot of things. It can be a game like chess or StarCraft. It can be a factory for like industrial robotics. It can be a fusion reactor. It can be anything that the agent interacts with and tries to control or tries to do something with. And then the most important part, of course, is the reward. The agent wants to maximize reward. Most of the rewards are extrinsic, so for an Atari agent that's hard-coded, maximize your score. It can be food, it can be water, but it's much more difficult for biological agents, so we often assume that a lot of rewards are intrinsic, and there's a whole field of research on that. So how do we solve the RL problem? The RL problem basically is you try to maximize rewards in an environment. So for the dog, he maximizes the treats. For the Atari agent, he maximizes the number of points. This is the RL problem. We maximize the points. The way we think about this is we say the RL problem has different components. The RL problem consists of a set of states, of actions, a transition function. The transition function basically tells me how does the environment change. If I play chess, if I move one piece from here to here, it changes the state. If I'm here right now, if I take an action, it will move the environment to a different state. And the transition function tells me how do the states change based on my action. So the transition function is a function that takes as input a state and an action, and it spits out a new state. It just tells me how I move through the states of my environment. And that can be a fusion reactor or a game of chess or whatever. And then we have the reward function, which just tells us when do I get rewards? Do I get a reward in this state? Do I get a reward in that state? And the last thing is the discount factor. And the discount factor basically tells us how much do I value a reward right now compared to a reward in the next state or the state after the next state. So you can imagine if I offer you 10 euros now or 10 euros tomorrow, most of you would probably pick 10 euros today, right? I could offer you 10 euros today or 11 euros tomorrow, and then the decision gets a little more complicated, right? Or I could offer you 10 euros today and 20 euros tomorrow, and then you might pick tomorrow. And exactly how much more I have to offer you tomorrow compared to today is your discount factor. So this just takes care of things that the agent might die and not ever reach the end of the episode or something like this. Yeah?
Do I need to know all of the states in advance? Can I plan for something like this?
We do assume that we do know all the states in advance. And obviously that's not true in most cases. But that's a simplifying assumption that we make. That's a good question. And then the last ingredient that we need for the Markov decision process, the MDP, is the Markov property. The Markov property basically says the next state depends only on the current state and action and not on the entire history. So if you imagine you're playing a game of chess, you want to figure out what move am I taking next. In theory, you need to know exactly what have I done since the beginning of the game. Where did I move? Where did my opponent move? And so on. You need the whole history. But once you think about it, if you only see the snapshot of the chessboard, you actually have all the information compressed in there. It doesn't matter if you came from the left or you came from the right, as long as the piece is there, this is all you need to know. This is the Markov property. So basically it just means that the next state, which depends on your current state and your action, and all the states and actions in the past is actually just dependent on the current state in action. So they are conditionally independent. So basically, what this buys us is that we can break down a really long and complicated decision process that has hundreds and hundreds and hundreds of time steps and only think about the one-step transitions. And that will make our life much easier. Okay, so these are the ingredients. We have the 5 tuple of states, actions, transitions, reward, discount, and we have the market property, and this lets us solve the RL problem. And we oftentimes talk about grid worlds like this. We have an agent that moves around, we have a goal state, we have a wall that the agent can't go through. So let's just, what's the state space here? What are the different states? Yeah.
And the position of the agent, so on the left upper corner and the right upper corner.
Exactly, perfect, those are the states. What are the actions? What's the action space? Yeah. Perfect. What's the transition model? It's a little harder to describe, right? Yeah.
Reaching the goal or not reaching the goal?
It's actually, yeah, it's actually more complicated. The transition model tells you, yeah.
Basically, which probability you reach which state given the previous state in action.
Exactly, exactly. So we have the previous states here, then we add the action as well, and that gives us a new state. So if you're in S0 and you take the action up or left, you go back to S0. If you take the action down, you go to S2. This is the transition model. And then here, this is an absorbing state because once we reach the goal, we never get out of it again. And then rewards say empty cell is 0, wall is -5, goal is +10. Okay, so in MDP terms, what is happening here is that the agent moves from this cell to that cell and gains a reward of 0. And here, in MDP terms, you can imagine, right? It's moving from here to here and it's getting a reward of 10. So I told you the goal of RL is for the agent to maximize reward. The way we denote this is we calculate a return. A return is the reward I'm getting in this time step, plus the reward I'm getting on the next time step, plus the reward I'm getting on the next time step. And each one of those will be multiplied with a discount factor to make sure that future rewards count less than current rewards. And now what you say is, in order to achieve this goal, the agent learns a policy. The policy is a probability over actions that I could take, given my current state, and I just sample one action from this probability distribution. The question is, how do we find this policy? How do we find this policy? How do we find a policy that lets us maximize the return? Trial and error, exactly. Because what do we do when we do trial and error? We learn. How do we learn?
What is bad, what is good?
Say again?
We learn what is good and what is bad.
What's good and what is bad, and how do we, like, what's the key concept that lets us learn what is good, what is bad? Reward prediction errors, because they let us learn
Change the policy.
how to?
How to change the policy.
How to change the policy? Okay, you're all like saying the thing without saying it. Yeah. Values, exactly. We need the values, right? Yeah. Exactly. You all said the right thing. I wanted to hear values. How do we find the policy? Using values. Because once we know what the values are of each state, we automatically know what the optimal policy is. Pi star is the optimal policy. Okay, this is a policy we want to find because that lets us maximize our returns. The optimal policy is super easy because once we know the values, we just pick the action with the largest value in each state, and that will automatically give us the optimal policy. I'll repeat that because that's crucial and it's also hard to wrap your head around. If we know the value of each action in each state, if we know the value of each action in this state, we just pick the best action, and if we keep doing that, we will find the best long-term policy. This is the magic of RL. What we want to do is we want to solve a really complicated problem where we might have to think 100,000 steps into the future. But once we have values, we only need to think one step ahead of time, and still we will be guaranteed to make the optimal decision in the long run. Yeah.
So is that pi star describing a single action or like a general policy with however many actions?
Yeah, it's supposed to be a general policy. And here I say my policy for this specific state. So say this is the pi star of state S0. So this state here, there would be one answer for that state, and there would be a different answer for that state. And then in general, a policy for a whole environment would just be the policy for each state. Does that make sense? Does that answer your question?
Yeah, right. So like it's like the maximization of Q with like all of the actions that we're going to take given that initial state. And that's the goal, is that it?
Yeah, so we basically start an episode and then we choose actions one after the other until we reach the end of the episode. And the policy determines what we do during this episode. And the goal is to maximize returns during the episode. So the policy describes the whole, everything that happens in this episode.
Okay. Yeah. And how do you decide how many actions happen?
That's in the MDP. The MDP tells us the action space. Yeah?
I think I understand the question. The policy always only gives you one action at a time. So you give it a state and you get one action. But you do that for as long as the episode runs.
Not necessarily the policy.
Yeah, but in that formulation, pi star of S is just one action.
So pi star is just one action.
No, pi is a policy, but for each state it gives you one action. And then you reach the next state, and then you can query the policy again. Does that make sense?
Pi star is kind of a function in the next state, and then gives you the one action you should make in that particular state again.
Do you want to say something?
I just want to say it's just a mapping from state to action. So it's a normal function that exists or the state and it gets out and epsilon, that's an action. And the policy is the function. That is like defined in someone.
We could understand that maybe with the example of the dog. So if the dog on the food and has many actions, this policy will go through all the actions and see which one was the one that has the highest value.
Exactly. Exactly. Okay, cool. Does it kind of make sense? Do you have more questions? Okay, great. Cool. So basically, we try to learn a policy, optimal policy. Yes.
I was just wondering if the goal is to maximize rewards, and then you do this 2 by 2 model to get to the goal, you either go right and then down, or down and then right.
Very right. Yeah.
So how do we decide which one?
How do we decide? So in the end, what will happen if you are this agent? You will learn one value for going right and one value for going down. What would those values be? What do you think? What would the correct values be? They are the same. Yeah, they are the same. So what you do in this case is your policy will be, let's see, your policy, where is it? Yeah, your policy is a probability distribution, so it will just probably be 50-50 at this point, and you will flip a coin to pick one. Okay, so now I will give you the proper definition of what a value is. So remember, we have calculated values this whole lecture already. You know exactly how to calculate values. You calculate an RPE, that's how you update them. This is the proper definition. This is what we actually try to achieve by doing this one step at a time process. What we really try to approximate is the expectation of the return. The return, remember, is all the rewards I gain in this episode, plus a discount factor. And this is the expectation of my return under a specific policy if I start from a specific state taking a specific action. Does it kind of make sense? What we're trying to calculate here? Yeah. It's called GT. For some reason, the return is called G. Here? So yeah, so this is just spelled out. So yeah, this is the expectation of GT, which is just RT plus gamma RT plus 1 plus gamma squared RT plus 2. Okay, so let's just calculate those for the two states here. What's the value here for this state? Let's assume the discount factor is 90, which we always do, or which we often do. What's the value of this state action pair? The value of state 0 and action rate, according to this equation. Huh? 0? Under a policy, the policy is go right and then go down, under this policy.
How much rewards was there?
Yeah, I told you once, so it was very quick. The reward is 10, hitting a wall is -5, entering an empty square is 0. Okay, yeah, it's 9. How do we do this? We take this equation here, right? We say, what's the reward that we're gaining right now? It's 0 plus the discount factor, which is 0.9, and the reward that we get in the next time step, is 10. So it's 0 plus 9, which is 9. So this is the target that we're trying to achieve. And if we do RL, there were like one-step equations over and over. We calculate reward prediction errors and we update it. We will eventually approximate this. This is what we want to approximate. Okay, let's do the same thing here. And what's the value, the state action values of the agent here? Of this state S1 and the action down. What's the value here? Okay, great. How do you calculate that? Exactly. And then nothing happens after. Okay, awesome. Does this make sense? What we're trying to do, the RL problem means maximize your return. This is hard to do because this thing is difficult. We need to look into the future. We need to do some kind of like really complicated research. When our search space is big, this will be super complicated. But this is what we're trying to approximate. And the way, because then we can get the optimal policy. And the way we approximate this is exactly what I've shown you before. We can't predict the future. This is hard to calculate. But we have access to our beautiful Markov property, which lets us do the little nice step-by-step updates. So there's one popular way of calculating values, which is called SARSA. It's an on-policy method. And this is the equation here. And it's very simple. It's very similar to what I've shown you before. We calculate a new value, a state action value, based on the old value, plus alpha, which now is our learning rate parameter, right? The scaling factor. In here, we have the reward prediction error, which will be reward minus old value, like before, right? Lambda minus the sum of all the associative strengths. It's just the same, reward minus value. You all recognize this, right? But now we have one more ingredient in there, and that is the value of the next state. So when I told you about the dog before, it was a one-step decision-making process. Now we have a multi-step decision-making process. We go through different states. And this is why we also add the value of the state that we go into our reward prediction error. So we say, maybe we didn't receive a reward at this time step, but at least we went to a state that has a higher value than the state we came from. And this should also count for something. And this whole thing together would be our temporal difference RPE. Once we have the sequence of actions, we call this temporal difference learning. And SARSA is very popular. The reason it's called SARSA is because what you do is you start in a state, you take an action, and then you go to a new state, you get a reward, and you take a new action, right? Like the agent starts from top left, goes to top right, goes down, state, action, state, reward. And if you just read that out, it reads SARSA. And this is why we call it SARSA. So let's just do this here once, just to show you guys that this actually works, that by doing SARSA, we can approximate this much more complicated expectation on the previous slide. So if you're here, let's just do the update for this guy. The value of this state, initially all the values of all the states are 0. So let's do a one-step update. What's the one-step update going to be?
0.
Why?
The next value is 0 and the return is 0 and then just adding the multiplying zeros.
Perfect. Exactly. So we start, all Q's are 0. And then when we update this thing, we get a reward of 0. This is the old value. We get a reward of 0. The next state is 0 because it said all Q's are 0. And the current state is also 0. It's just 0. Okay, how about this one? What if we update the value of this state? Yeah.
Yeah, 0 plus alpha times the reward plus gamma is not existent because that's the final state minus 0, so and which is the alpha times the reward. That's the new.
Cool. So we get a reward of 10, say. So is 0.5. Cool. Does it make sense? We get a reward, a big reward here. Nothing happens in the future. Okay, so now the interesting thing happens. If you go back to this state, now we have those values. So the same thing happens. The same exact thing happens. We go to an empty square where we don't get a reward. But this time the update will look different. What's it going to be? Okay, I already heard somebody say it. So it's 2.25 here. We have an old value of 0. We get a reward of 0. But this time we move to a state that has a value of 5, these 5 here, and the gamma discount factor is 0.9. I did this at home. I hope the numbers work out, but this is 2.25. And now if we keep repeating this, you see where those values will asymptote, right? The value of this state here, where will it asymptote if I repeat this 1,000 times? Yeah.
Originally, even the goal state is at the 0, right? So it's almost like I have no idea that that is the goal state.
Yeah. Yeah. If I keep doing this, yeah.
It's reaching 0.
This one?
No, the one from the start to the right.
This is initially 0, yeah. This one. Okay, so we have the discount factor in there, which is 0.9. So it will asymptote at 0.9 times 10. Sorry, is this confusing? So where will this value asymptote if I repeat this 1,000,000 times? Oh, sorry. It's based on alpha. Yeah. Sorry. Yeah, 10. Yeah, I think you're right. 10. 10 is actually the right answer. Sorry. Okay, 10 is the right answer. So this will have a value of 10. And then where will this guy asymptote? 9, exactly. And if you go back here, this is exactly the right answer, 9 and 10. This is exactly what we get when we do this more complicated, looking into the future, super complicated, tree search, impossible thing. And if you just do this one-step update, which is super simple, we get the same answer. And this is the magic of RL. Okay, cool. And Sarsa is one way of getting those values, which is really handy because it's really easy. I wouldn't tell you there's a non-policy control method if there wasn't also an off-policy control method. I won't go into details, I just want to tell you that there are on-policy methods and off-policy methods, and they have different advantages, and people use them in different scenarios. Reinforcement learning is used in the real world. It has solved problems. It also is an active field of research because a lot needs to be done better to make it really work. Do you have questions? Yeah.
Just for one example, one of the examples on the previous slide, is there RL user personalization beyond menus?
I don't know.
That's fine.
I wish I knew. I don't. Okay, I want to get through neuroscience, and then probably we will leave it there. There's a neurotransmitter that's called dopamine. It's important for cognition, memory, attention, movement, sensory stimuli, pleasure, reward, addiction, emotion perception. Dopamine is really interesting. People have done a lot of studies on this. And it is essential for the theory of reinforcement learning. So in a really famous study, people have recorded from monkeys, have recorded dopamine neurons from monkeys as they were doing a conditioning task like this. And these are the traces of the dopamine neurons. So pretty much, if you don't show a CS, if you don't show the whistle, your dopamine neurons will just not do anything. And if you show the reward, they will fire like crazy, which fits with this view that dopamine is somehow related to reward. But then what they saw was something really interesting, and that is that when they showed the CS, dopamine neurons were firing like crazy. And if they then show the reward, dopamine neurons are not firing at all. So this is confusing. And then third piece of the puzzle is when they show the CS, again, they get a lot of firing. And when they omit the reward, so they don't give the dog the food that he's expecting, we have this dip in dopamine firing. So people are kind of scratching their heads and trying to figure out, what does dopamine firing represent? What do you guys think? What does dopamine firing represent? Yeah.
The sign of the rewards.
Second?
The sign of the rewards.
The sign of the reward.
The rewards, so there will be soon incoming rewards.
There will soon be coming rewards. Yeah? Reward prediction error. Think about it. Yeah, it's the expectation of the reward. This is the reward prediction error. So it's the discrepancy between what you think you will get and what you get. It's exactly the temporal difference reward prediction error. So it's not as simple as just a reward. So to convince you that this is true, let's just walk through this example. So for temporal difference, we need to know what the states are. So we have an ITI state where nothing is happening. And after we see the conditioned stimulus, we move into a conditioned stimulus state. And then once we have seen the reward, we go back into the ITI state. ITI just means intertrial interval. So it's like the state where nothing interesting is happening. And same here, we start from the ITI state. Once we see the CS, we move into the CS state. And then if you don't get a reward, we still move back into the ITI state. The interesting thing is happening here. We started in an ITI state, then nothing happens. So we stay in the ITI state. Then we get a reward. And what happens after a reward? We go back to the ITI state. So if we now, so let's say we have already conditioned our dog. So what are the values? What's the value of the CS state? It's 1, exactly. Because the dog knows whenever the CS comes on, he will get a reward. What's the value of the ITI state? 0, because nothing interesting ever happens after the ITI state. Okay, cool. So now I just put those triangles here to know what we're talking about. So let's calculate the RPE here. The RPE is reward plus gamma times value of the next state, which is the ITI state, minus the value of the previous state, which also is the ITI state. So the RPE here is yes. The ITI state is this state here. It extends from here to here. It just means that it's the state where nothing interesting is happening. It's the intertrial interval. So it's, huh? Yeah, before the stimulus comes on. Yeah.
So this is just one.
So at the red triangle, there's no reward. So we're just talking about like this time window here. So there's no reward. Yeah, 0, exactly. So we don't get a reward here. And we move to a state that's not interesting. And we come from a state that's not interesting, so RPE is 0. And indeed, there's no firing here. Now let's move to this purple state here and calculate the reward prediction error. In the same way. So now we have an immediate reward, and we move into the ITI state, and we come from the ITI state. 1, exactly. We get a reward, and those two are 0. And this explains why there's so much dopamine firing here. It matches exactly with what the TD RPE tells us. And if you go through the other examples here, we can calculate the RPE here. Reward plus now the value of the CS state minus the value of the ITI state, because we move from the ITI state to the CS state. What's the reward that we observe here? 0. Reward is 0. There's no reward given. We just see the CS. We just hear the bell. Yeah. 0.9, exactly. Because we don't get a reward. No reward is being delivered. We just hear the bell. But we move into the CS state, which we said has a value of 1, and we came from the ITI state, which has a value of 0. So we have a big RPE, which is surprising. There's no reward being delivered, and still there's a big RPE because we move into a state that we know is very valuable. And this is exactly where the dopamine neurons fire a lot. And now let's figure out why they don't fire in this state here when the reward actually gets delivered. Same, we can calculate the RPE. So we do, what's the reward in this case? 1, exactly. We do get a reward this time. We do get the food. What's the value of the ITI state? 0. What's the value of the CF state? 1. And now when you do the math and we subtract those, we have an RPE of 0.1. But it's super, super, super minor, and we don't actually see much happening here. And you can do the same thing for the last example. Same thing here. We have an RPE here. And then exactly for the other one, you expect a reward, you don't get a reward, so you have a negative RPE, and this is why the firing rate dips. And when people saw this, they were very happy, because they said, dang, we have this TDRL theory, which tells us how to calculate reward prediction errors. And we see exactly the same thing in the brain. It's almost as if the brain was doing RL. And that would be very cool, because then we can really understand what's going on in the dog's mind as he's learning all those tricks. Because it seems like the same concepts that people have come up with and that they use in robotics and chess and StarCraft and whatnot is all present here in the dopamine firing, in the midbrain dopamine activations. Okay, and I think I will just skip to my conclusion slide. Let me see if I can find it. Is there anything more interesting? Basically, okay, let me just say one more thing that I wanted to say, and that is, you can now do experiments. You can start here, say what are actions, what are states, what are rewards, and you can set up human experiments, and people do that a lot. It's a very interactive research area where you give people the choice between the blue triangle and the red square or whatever, the blue circle and the orange triangle. And then you use the same equations to predict human behavior. So the way this works is you find a model, you fit the model, you expand the model, you compare the model. So if you want to understand a cognitive process, you take a model like RL and you fit it to your data set by fitting some pre-parameters, like the learning rate I showed you before. You make it bigger or smaller until it captures your data set as good as possible. And then what you will end up with is some variance that you haven't explained, some systematic variance. And then you add little pieces to your theory. For example, there's no forgetting in my model, right? You can say, oh, there's forgetting. You can say, oh, I treat positive and negative rewards differently. And you add things like this. And then you do model comparison. So you say, which of those models explains most variance? And then once you have done this, you have a model, you have a shape of what this process looks like. You have an understanding, and you can fit the parameters. This is cognitive modeling in a nutshell. You take one of those theories, you apply it to your data set. And I think this is pretty much it. A lot of people are doing computational modeling. It's really a hype right now. There's a lot of open questions. And if you want to learn more, I put a lot of resources here.